Okay, now, in the same way that we started with the linked version, the classic linked version of the linked list, and then we did the composite state pattern version of the linked list. Now that we have done the linked version of the binary tree, we will do the composite state version of the binary tree. And here it's called BiTree CS for composite state. Now, what's the idea behind the composite pattern? Do you remember what is it that made our composite state linked list a composite pattern? Yes.
Well, for the list, it was the list points to a node, which points to a list. So for the binary tree, the children are going to point to binary trees.
That's exactly right. So what happens is, in a list, instead of having underscore next be a pointer to a node, like we had with the linked version, we didn't call it underscore next instead. What did we call it? We called it underscore what? Rest. And underscore rest was a what? It was a list. So now what's going to happen, it's the same thing. In a non-empty node, underscore left now is not going to be a pointer to a node. Instead, underscore left will be a what? No, it will be not just a pointer to a binary tree. It will be a binary tree. Are you with me? Is everybody clear? It's not a pointer to a binary tree. It is a binary tree. And underscore right is a binary tree. So here in figure 8.24 is the composite state pattern for a binary tree. Now this should look familiar. This pattern should look familiar. This layout of the classes and how they are related to each other should look familiar. So let's review it. And the one up on the left, the upper left, is BiTree CS. Okay, so that's binary tree composite state pattern. And how many attributes does it have? One. And what's it called? Underscore what? Root. And furthermore, what is the type of underscore root? It is a what to a what? Pointer to abstract node. Are you with me? And what does that little diamond, solid diamond, represent? What kind of a relationship is that? That's called what? Starts with a C? Class composition. So is that has-a or is-a? Has-a. So a binary tree has a abstract node. Are you with me? Pointer to an abstract node. And then this big block over here on the right is an abstract composite state node. So that's an abstract node. Does it have any attributes, yes or no? No. And furthermore, some of the methods for the binary tree have identical methods for the abstract composite state node. But some of them are slightly different. Those ones that are different have an additional parameter named what? Owner. Are you with me on that, with that? And why do we need those ones that have owner? Those ones where the binary tree calls the node version and has owner. Why do we need that owner? When that method does what to the data structure?
Changes the class.
When it changes it, that's right. Those are for the ones, because these are mutable. These binary trees are mutable. And so in order to change the state, it needs to change, in order to change the state, you might have to change the kind of node that underscore root points to. So owner needs to pass itself so that the node can have access to the underscore root of the owner. Okay, and all, now does this familiar? Okay, we've seen all this before, so now we'll get it all reinforced. Okay, and furthermore, the abstract composite state node, that's abstract, right? And those slanted, notice that all those methods are all slanted. Okay, so all of those methods are abstract. That means that they're not implemented in a CS node at all. And then what's the open inheritance? Is that has-a or is-a? Is-a. And so what do we see inherits from that? NECS node, that's a non-empty composite state node. And our old friend empty for empty, yuck yuck. Empty, okay, that's also inherits from an abstract node. And so each one of these, we didn't repeat them here because then the diagram would be really big, but each one of these does what? Implements, each one of those implements the abstract method specified in ACS node, in the ACS node class. Are you with me? And now, how many attributes does the empty CS node have? None, because it's empty. So it doesn't have any attributes. It's just... On the other hand, if it's non-empty, now before, what did a non-empty one have? With the list, what did a non-empty node have? It had a data and a rest. But now, what does our non-empty node have? It has a left, a data, and a right. Exactly. Are you with me? Is everybody clear? And then, why do we have that? What's that relationship going back up to there? Composite, yeah. Class composition. Yeah. So, and what does that say? That's saying that a what? A non-empty CS node has a what? Has a binary tree, because its left is a binary tree and its right is a binary tree. So it has a binary tree. Yeah? Okay, so does everybody see? This is all familiar now. So now we're going to reinforce what we learned before. Okay? So on this next slide here, we have the actual code that has the attributes. All right? And so we see that our class ByTreeCS, it has, its attribute is _root. So this is very similar to what we did with the linked version. And what is that root? That root is a what? What does it say there? It is a what to a what? Pointer to an abstract node. Are you with me? And then I didn't show the abstract one because it doesn't have any attributes. I didn't show the empty one because it doesn't have any attributes. But the non-empty CS node, and by the way, what is that colon? What is this C++ colon right here mean? Oh, little C++. What's the third goal of this course? What does this colon mean? Say it again. Yeah, inherits. That's inheritance. Is everybody clear on this? This colon is inheritance. So the non-empty CS node inherits from an abstract CS node. All right, is everybody good? So there's the inheritance. And then here is, and so what do we have? We have _left has, what is it? It is a what? Binary tree. And _data has type T, and _right, what? Is a binary tree. So that's what, so here, boom, that's what makes it composite. That's what's different now. So before, you know, a few minutes ago when we were talking about linked lists, I keep saying lists, linked binary trees, and we had to check, and you know, we had this node version, we had to check pointers, blah, blah, blah. Now, and furthermore, once we got into a node and we did something recursively, it was always the node version calling the what version? The node version. It's never the node version calling the binary tree version, because once you're in a node doesn't have anything to do with binary tree. But now what can we do? Now what can our code do? Our code can use _left, can call a binary tree version of a method through _left. You can say _left and then call a method for a binary tree. So we can go back and the tree can, so everything's going to be, so now what does this match? This matches the mathematical definition, or the formal method's definition of a binary tree. And so here in figure 8.25, it's just, does this look familiar? Yeah, I mean, right? This is, so now let's take a look at figure 8.25a, a detailed rendering of a binary tree and a node. So So here on the very left, you have my tree is a tree, and what does it have inside of it? An underscore root, and what is that underscore root? It is a what to a what? It's a pointer to a node. So that's what a tree looks like. A tree looks like a rectangle that has inside of it a pointer to a node. Are you with me? And now, when we take a look at the node to which it points, the node to which it points is called star mytree._root. Yeah? Are we good? And now look what mytree._root arrow left is. Now what is it? It's underscore left is not a what?
Not a node.
It's not a point. You're right. It's not a node. It's not a pointer to a node. What is it? It is a what? It's a binary tree, because that's what the binary tree looks like. Are we good? Does everybody see the difference between the composite pattern and just the regular old one we had before, where we had to check for null pointer, blah, blah, blah. Now we don't have to check for any of that stuff. All that stuff's going to be taken care of for us. I tell you, once you sort of use this pattern, you wonder why anyone would ever do it the other way. I mean, you'll see the code will be so much easier for this. All right, and similarly for the right. Okay, so mytree._root arrow right is a binary tree. Okay, and then mytree._root arrow right ._root, that's a pointer to an abstract node. But here again, we're going to abbreviate. Now see, it's a little confusing because we use the same abbreviation whether we're doing the composite pattern or whether we're doing the linked pattern. See, so it's ambiguous. Anytime you have a drawing, but this is very common. It's very common to illustrate linked data structures this way. But you have to be aware that this is an abbreviation, and that really, if you were to do it more accurately, all of them would be done like that. And so whenever you're coding and you say, well, what about, is it dot or is it arrow, and what is this and where's my environment? I think it's helpful to see the structure the way it is in part A. Are we good? Okay, so here let's start doing methods for output and characterization. So look here in figure 8.26. Check out how easy this is. This is pre-order. Oh, by the way, I could demo it, but why demo it? It would look exactly the same. You couldn't see, you see what I'm saying? The user can't tell the difference. So, there's no point to demo. Okay? So check out pre-order. So here, the main program says, hey, tree, do a pre-order. And the tree says, oh, I need to do a pre-order. And he says, what the heck am I supposed to do? I don't even know if I'm empty. I don't know if I should do that. So what does he do? He says, I don't know, but I have a what? I have an underscore root. And so what do? I say, root, you do it. I'm the boss, you're my subordinate. You do it. You're a node, you know how to do it. Now, which one of those is going to get called?
Depends on
polymorphic dispatch. Okay? So we don't have to check to see if it's empty or not empty, right? So if it's the empty one, what does he do? Nada. I don't have anything to print out. I'm empty. So it just returns. But on the other hand, if it's not empty, then what do? Pre-order, we visit the data. So we stream underscore data in some spaces to OS. And now what is underscore left? It is a what? It's a binary tree. So what are we calling? The binary tree version of in order. Is that slick? Of in order. And then call the binary tree version of pre-order on underscore right, with underscore right. Now that's just neat. No checking for null, blah, 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 blah.
So with the underscore left dot pre-order, anything goes up to the first.
Yes.
And it goes through it all again.
Yes. Yeah. It actually does go up through that, and then that one does call root arrow pre-order, and then it will polymorphically do. Yeah. Yeah. That's a good point. Okay. And now look. Now check out how easy isEmpty is. Look, so the main program says, hey, are you empty? Is empty? Are you empty? And the guy says, I don't know. Ask my root. Here, root, I'll return what you tell me to return. And what happens? Polymorphically, if it is empty, just return true. Otherwise, return false. We don't even have to have an if statement. Is that slick? Polymorphic dispatch. Okay? So now let's review. What is it that makes up an environment? The environment, when you are coding a method for a class, what determines what you have access to? What determines your environment as a coder, as a programmer? When you are programming code for a method of a class, what determines that?
The attributes.
The attributes and the parameters is correct. Are we good? It's the attributes and the parameters. So, look, do you see that in part A of this figure, that's the environment of a binary tree. Why is that the environment of a binary tree? Because what attributes does a binary tree have? It has underscore root. And you see, and by the way, you see that is empty? How many parameters does that is empty have? None. So therefore the environment of your code, when you're coding the root, the environment is the only thing you have access to is underscore root. You don't have a parameter. And what is that cloud? What is that root pointing to? An abstract node. So that's the environment of a binary tree. What's the environment of the empty node?
Data left and right.
The empty node.
Nothing.
Yeah, just nada. So there's the empty node. And now, what's the environment?
Data.
Yeah, underscore left, underscore data, and underscore right. But it can also use the fact that those are binary trees. Underscore left is a binary tree. But here it doesn't care, right? It just knows right off the bat. Boom. Is everybody good? And here is method left. So what left does is it returns the left child of a tree, okay? So, can you see what the type is? The type returned by left, it's a by tree CS what? Ampersand. So it returns a reference. That ampersand is a reference. It's like a reference variable. Okay. So the main program says, hey, I need a reference to your left. And the tree says, I don't even know if I'm empty or not. I don't know if I have a left. So what does he do? He says, return root. You take care of it. Return root arrow left. And now what happens is, the empty version of root arrow left says, wait a minute, I'm empty. You don't have a left because I'm empty. So it implements the precondition. And then what does the underscore left, what does the non-empty version do? What was the environment of that non-empty version? Yeah, see back here on part C, it has an underscore left data, and so it just returns what? Underscore left, because that's what was wanted. That's what the main program wants. So that's how you can have access. You can have access to the left child of a tree through left. That's how you access the left child. So now it's not pointer, dot, arrow, blah, blah, blah. You see what I'm saying? It's just left. And it's a function. So with parentheses. It's a function call. Is everybody clear? The same way with right. And now look, you guys, here's num nodes. Look how easy num nodes is. Now look, here's like that picture that I think I had a similar picture on the board the other day for the linked version of the binary tree. So num nodes, look. So here, how many nodes does a tree have? Well, so the main program says, how many nodes do you have? Num nodes. And the tree says, I don't know. I don't even know if I'm empty or not. So what does he do? He does return underscore root arrow num nodes. And then what happens? Well, if that tree is empty, we return 0. Otherwise, now, if it's not empty, what do we return? 1 plus the number of nodes in the left subtree, because it is a tree, plus what? However many there are in the right, as shown in this figure. So it's 1 plus however many there, plus however many there. Now what could be, What could be simpler? Are you with me? Is that slick? I mean, that's the mathematical definition of the number of nodes. If the tree is empty, it's 0. Otherwise, it's 1 plus the number on the left plus the number on the right. Now, and here is Max. We'll end with Max, but now, unfortunately, Max doesn't have any really slick. Max is. This is the same. We went through this code. This is the same. This is very similar to the code that we did before for Max with the linked version. So the main program wants to know what the max is, and the tree says, I don't know what my max is. I don't even know if I'm empty or not. I don't even know if I have a max. So he polymorphically calls max, and then if max precondition is violated, if it's empty, and so he implements the precondition. And now, on the other hand, if it's non-empty, then we do this logic. I think we went through this logic. We went over this logic for max before. But look what's different about it. What's different about it is, you see, we don't check to see if left equals the null pointer. You see, how do we check that? We say what? Underscore left dot is empty, because underscore left is a tree, and so that calls the tree version of is empty. Are you with me? So anyway, but this logic I think we went through the other day. With this, we had nested trinary operator thing. Okay. All right. And then equals is going to be an exercise for the students, so we'll start there on Thursday. All right, good deal.